You know, they're all around us, but they feel like nothing, right? I'm talking about gases. And what's wild is that the story of how we finally got gases is actually the story of how we unlocked modern chemistry itself. It's this incredible revolution, one that started with a genius and ended, well, tragically.
Yeah, those are some heavy words, right? They were from a mathematician, and he was talking about his friend, one of the greatest scientific minds ever, Antoine Lavoisier. And while, yes, he was famously a victim of the French Revolution, his real revolution, that happened in the lab. And it was about to change, well, everything.
Think about it. Before Lavoisier, chemistry was kind of like magic. It was more art than science, like cooking without a recipe book. But he came along and changed the whole game by asking one simple but totally revolutionary question: how much? By getting serious about measuring gases, he gave chemistry its backbone, actual numbers, solid principles, the stuff of a real science.
So, how in the world did one guy start a scientific revolution with something we can't even see? Let's dive in and find out. Okay, so they call him the father of modern chemistry, and for good reason. The guy was brilliant. He used his super precise scales to prove that matter is never actually lost, it just changes form. And he was the one who figured out that a burning candle and a breathing lung are basically doing the exact same thing, using up oxygen. This was huge. I mean, this was the bedrock for all of modern chemistry. All right, if you're gonna build a whole new science, you're gonna need some new tools. But for the science of gases, the most powerful tool, well, it isn't something you can hold. It's not made of glass or metal, it's an equation. Just one beautiful, elegant equation. And here it is, the ideal gas law. PV equals nRT. Seriously, this thing is like the Swiss Army knife for chemists. Just think about what it does. It connects pressure, volume, temperature, and the actual amount of a gas. Four totally different things, all in one simple formula. And the best part? It doesn't care if you're talking about helium in a balloon or chlorine in a tank. It just works. It's the universal key. Okay, so we have this powerful formula. That's great. But what can you actually build with it? What can you do? Well, it turns out a lot. See, the real magic here is how flexible this law is. You can just move the pieces around. If we rearrange it a bit and mash it together with the basic formula for density, boom, we've just built a brand new tool. All of a sudden, you can figure out how heavy a gas is without ever needing a scale. All you need to know is its pressure and temperature. How cool is that? And we're not done. We can flip it around again. If we rearrange the equation to solve for molar mass, that's the big M right there, we can do something that feels like science fiction. We can identify a total unknown. So say you capture some mysterious gas. You just measure its pressure, volume, and temperature, plug it into this formula, and out pops its molar mass. That's basically its unique chemical fingerprint. You've just identified it. Now, the ideal gas law is awesome for a single pure gas. But let's be real, the world is messy. What about a mixture of gases? Like the air we're all breathing right this second? For that, we need to pull another tool out of the toolbox. And that tool is Dalton's law. And the best thing about it is how beautifully simple it is. It basically says that when gases are mixed together, they don't really bother each other. It's like each gas thinks it has the whole container to itself. So if you want to find the total pressure, just add up the individual pressures. That's it. It really is that straightforward. Okay, let's make this super clear. Imagine we've got a container with just gas A inside. We hook up a gauge and it reads 300 kilopascals. Now let's take an identical container, but this time we fill it with gas B. Its pressure? 450 kilopascals. And one more. Same deal. Container with gas C. This one's at 600 kilopascals. So here's the big question. What happens if we cram all three of those gases into the same container? Well, Dalton's law says you just add them up. So 300 plus 450 plus 600 gives you a grand total of 1,350 kilopascals. See? It just makes the complex simple. All right, so far we've been talking about gases that are just hanging out. But chemistry is about action, right? What happens when gases are part of a chemical reaction? Well, it turns out there's a really elegant shortcut for that too. This awesome shortcut exists because of something called Avogadro's law. And the idea behind it is kind of profound when you think about it. It says that equal volumes of any gas, doesn't matter what it is, as long as they're at the same temperature and pressure, have the exact same number of molecules. This is a game changer. It means we can skip all those tedious steps you see on the left. No more converting from mass to moles and back again. We can just look at the balanced equation, the reactions recipe, and use its ratios directly with volumes. It's amazing. Let's try it out with something real, like burning propane on a grill. The balanced equation is our recipe, right? It tells us that for every 1 molecule of propane, we need 5 molecules of oxygen. Thanks to Avogadro, we can just swap the word molecules for volumes. So 1 liter of propane needs 5 liters of oxygen. Simple. So if you've got, say, 2.7 liters of propane you want to burn, you just multiply by 5. You're going to need 13.5 liters of oxygen. Done. No crazy math needed. Now, all these laws, they're not just for homework problems or chemists in a lab. They are absolutely critical for understanding the world we live in, especially that thin, fragile blanket of gas that makes life on Earth possible, our atmosphere. It is pretty mind-blowing when you stop and think about it. Less than half of 1%, less than 0.5% of the air is made up of what we call greenhouse gases, like carbon dioxide. But that tiny, tiny fraction works like a planetary blanket. It traps just enough heat to keep Earth's average temperature about 30 degrees Celsius warmer than it would be otherwise. Without it, we'd be a frozen rock. It's absolutely essential for life as we know it. But here's the thing. The makeup of that tiny fraction is changing. For hundreds of thousands of years, the amount of CO2 in the atmosphere went up and down, sure, but it stayed below 300 parts per million. Now, look at where we are today. We've blown past 400 ppm. And as you can see, this isn't some gentle natural curve. It's a vertical spike, something the planet hasn't seen before. So why the huge increase? Well, the source material points to strong evidence linking these higher CO2 levels directly to human activity. Specifically, the burning of fossil fuels is identified as the driver for about 3/4 of this recent jump. This has pushed CO2 concentrations to the highest they've been in at least 800,000 years. So we've come a long way, from Lavoisier making his first precise measurements in a lab, to us today using satellites to measure our entire atmosphere. The laws of gases, they've given us incredible power. The power to predict, the power to create, and now, the power to see our own impact on a planetary scale. The science that all started with that one simple question, how much, has led us to the most critical question of our time. Now that we know all this, what are we going to do with that knowledge?